Hey guys, welcome back. In today's video I'm going to rebuild the battery of this old electric drill. Now this thing is at least 10 years old and I think it's closer to 15 years. At the time I bought it for a few minor projects and then I didn't need it anymore. But approximately 4 years ago when I started building things again, I got it out of the closet, but the battery was dead. And even at the time it wasn't really great. And at the time I decided to not rebuild the battery with cells, or I thought about using 18650 cells at that time, but I decided against that because for one I was inexperienced with using these cells, and number two, from experience with the old cells, this thing wasn't really running for a long time. So I decided to attach a cable, goes directly in here to these contacts, and an XT60 connector. It's overkill, but I decided to use this and power it just directly from the power supply. But there are a few things that are not really good, and number one is you have a cable, which makes it really inconvenient to use the drill, and number two, the position underneath here. I can't let it stand like this. It always has to balance on the edge of a table, and that's not good. But now that I'm more experienced, I'm going to build a 3S2B lithium-ion battery from some 18650 cells, and I hope all the cells do fit inside of here. I have to test that. And obviously, whenever you use any lithium technology battery, you also need a BMS that makes sure that you don't over-discharge the cells. Now the drill itself might be really old, but the motor inside and the gear and everything is totally fine. I use it powered from bench power supply for like 4 years right now, and it still works totally fine. It's a bit heavy, it's old technology. So before I go ahead and build this new battery, let's take a look at a few basic things. So as I said, I'm going to build a 3S2P battery, which means 3 series and 2 parallel, which will look like this in the end. So we have 3 series and 2 parallel. Connecting cells in series means that the maximum voltage per cell is 4.2 volt. The nominal voltage, which is the voltage that they are at for the most part, is 3.7 volt. And the minimum voltage, safe minimum voltage, is I think around the 3.2 volt range. And connecting 3 in series means we have to multiply this number by 3. So we have 12.6 volt maximum. We have 11.1 volt the typical voltage, and the minimum voltage is 9.6 volts. Connecting 2 cells in parallel means that if each cell, for example, has 1200 milliamp hours, connecting 2 in parallel, we get an overall capacity of 2400 milliamp hours. Connecting 2 cells in parallel does not only mean that your capacity or your milliamp hours is higher, but also it means that the load per cell is lower. Let's say in this case, I know for a fact that this drill will pull 5 amp. So if there was just a single row of 3S cells, so this row over here, each cell would have to deliver 5 amp of current. But connecting 2 in parallel, each cell only has to deliver half of that. Or if there were 3 in parallel, only a third. 4 in parallel, only a fourth. So this is also a thing. Not only does the capacity in milliamp hours rise, but also the current draw per cell drops. Whenever dealing with lithium technology based batteries, you have to use a BMS. And this one over here is a really crude BMS that has just a few functions. And this thing has overall 6 connections. We have the positive connection over here and the negative connection over here. These connections do go both to the motor and also are the ports for charging the cell. So you have to have 2 connections for motor slash the switch and also your charging. You have to charge with a maximum voltage of 12.6 volt, so each cell goes to 4.2 volt, or a lower voltage. But you have to keep in mind, low voltage means lower voltage per cell. You cannot give in a higher voltage because this thing has no internal regulation for the voltage except for the balancing part of this BMS, because it's capable of balancing with a few milliamps all of the cells, so all cells have the same voltage. If they do not have the same voltage, they could get damaged over time or overheat or explode in the really worst case. But essentially they would just go like once for example, if you lose, well, actually if you lose any cell, the capacity immediately drops down to a single 3S configuration, and the only remaining cell, let's say in this configuration over here, we're losing this cell over here. This cell would have to deliver the maximum current of like 5 amps, and therefore this would be used more than all the other cells, so this could break down even further. Yeah, so basically you have to have this balancing feature in the BMS. We have a 0 volt connection, we have a 4.2 volt connection, 8.4 volt connection, and a 12.6 volt connection. And what this means, if we go in here, let's say this over here is our negative and this over here is our positive. This would be the 0 volt, this would be the 4.2 volt, this would be the 8.4 volt, and this would be the 12.6 volt. But there's also another thing that you have to keep in mind, and that is to use the right BMS or change one of these resistors surrounding the microcontroller so that the low voltage protection is in the right range. For example, this thing over here has a low voltage cutoff at 2.5 volt, and that is because this thing expects you to draw always a higher current, therefore you have a bigger voltage drop. And this thing, if you use, I think it was 6 amps, it cuts at 2.5 volt per cell, it goes back up, or should go back up to 3.1 volt. That's what the datasheet of this BMS said. But if you have a different use, you're not using as much current, or you want a different voltage, you have to take a look into the datasheet and change one of these resistors that surround the microcontroller, or buy a BMS that is already set for your preferred low voltage cutout. And that is essentially everything that you need to know if it comes to lithium-ion technology batteries. I hope I didn't forget anything, but if you did, you can leave a comment down below and tell me what I forgot. Now, but don't comment that I didn't explain everything. This was not meant, this was just meant for this particular case if you are converting an old battery. So first I'm going to cut off this XC60 connector. I will try to get these cables inside. Now these cables are totally fine. They are 2.5 square millimeter cables, and if you compare them to like 16 AWG is 1.6 square millimeter, so they are a bit thicker and totally fine for this. Now let's take a look if actually 6 cells do fit inside, and yes, they do. Perfect. Let's see, I'm going to make pairs of 2 and solder everything up, connect the BMS, and then we will test the drill. Okay, so my battery died and I decided to finish the battery off camera. I inserted a charging port. This is a temporary solution because originally I wanted to use the original battery charger from this drill, but I didn't find it. So I decided to cut in a hole into the case, insert an XT60 connector, and for now this is just friction fit with a bit of cardboard around, friction fit inside. If this screws down, this is really not coming off. And beside that, one thing before I close it up and test the battery, I inserted some of these foam strips, and that is to dampen any vibration that comes from the drill to the battery. Vibration could cause the solder joints to break at some point, and also to prevent the battery from sliding within the case. And now I can close it up and test the drill. Okay, here's another shot of the battery right now. We do have the two holes on the bottom. That's not a big deal. You won't have these if you upgrade a drill. This is just the two cables that I use to power it. And on the back side we now have this XT60 connector. This is not a problem. The drill will, for the most part, stand up like this. I can now charge it from this temporary solution and also use the battery externally without having to get the voltage from these contacts. I can just use a XT60 connector. Now let's insert a battery and see. That sounds good. Now before I go ahead and do anything with it, I would like to take another look at the current voltage. Oh, by the way, if I oh sorry guys. Now if I read the voltage and I apply a load, you can see how the voltage drops. And that was with just my bare hands. Let's take another look. And that's how much the voltage drops off the cell when you apply some load. Now I will remove the connector and ouch, I just hurt myself. It slightly hurts, not that much. I shouldn't have used it on the high setting because this is much softer. Okay, so for the remainder of this video I will have this white tape on my finger to protect the wound. I will deal with it later, and I have the perfect test subject. This over here, this is just a piece of scrap wood where I attached some sandpaper so I can sand something down, and I have to replace this anyway. So let's just remove the screws as a first small test. Okay, so that's not a problem. That was expected because they are loosely screwed in. And now let's just drill into the wood a few times. Oh yeah, that's a small problem with this drill. The chuck is not really strong. Yeah, I think that's okay. It works. Now, let's take a look at the cell voltage. I would like to know how much it already dropped. 11.28. So after 2, 4, 6, 8, 9, 11, 13, 15, 17 holes into medium hard wood, we dropped 0.2 volts. So this should give you an indication on how good the cell actually is. Well, there you have it guys. I hope you liked this small project, and if you did, please leave a like, comment down below, and other than that, thanks for watching and see you next time. Bye!